Welcome to this explainer. Okay, so today we're taking a super dense 60-question technical guide and turning it into a fast-paced masterclass that builds your electrical engineering knowledge completely from the ground up. Whether you're prepping for a high-stakes hot seat interview or you just want to really solidify your understanding of how the modern world is actually powered, you are in the perfect place. Let's cut right through the noise and get straight to the crucial concept.
Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
Here's our roadmap for today. We're going to cover basic electrical fundamentals, the magic of transformers, electrical machines and motors, power systems and protection, and finally wrap up with some practical engineering scenarios. All right, let's jump straight into section 1, basic electrical fundamentals. Now, this first concept is a classic interview trap. You know how actual electrons physically move from the negative terminal to the positive one in a metal wire? Well, here's the catch. We always define the conventional current direction the exact opposite way, from positive to negative. It's honestly just a historical quirk, but knowing this distinction right off the bat shows you really know your stuff. So, zooming out a bit, let's look at how that current actually gets delivered. We've got direct current, or DC, like what you find in a battery. It maintains a constant magnitude and direction, but alternating current, or AC, periodically changes both. So why on earth does our entire power grid use AC? Simple. AC voltage can be easily and economically stepped up or down for long-distance transmission. It's an absolute game changer. Which brings us to a really common safety question that trips up so many beginners during interviews. What actually is the difference between the neutral wire and the earthing wire? I mean, they both seem to just go to the ground, right? Well, here's the deal. Neutral is absolutely required for the circuit to even work. It provides the normal return path for current to flow. Earthing, or grounding, on the other hand, is purely for safety. In a normal, healthy circuit, that earth wire carries zero current. None. It only kicks in to carry fault current safely into the earth if something goes horribly wrong, like an insulation failure. So just remember, neutral is for operation, earthing is for protection. Moving right along, let's get into section 2, the magic of transformers. You know, it's pretty amazing how simple this static device actually is. A transformer works entirely off Faraday's law of mutual electromagnetic induction. Basically, you apply an AC supply to the primary winding, which creates an alternating magnetic flux in the core. That changing flux then links over to the secondary winding and induces an electromotive force, or EMF. This lets us smoothly transfer power from one circuit to another, usually stepping the voltage up or down in the process. So, knowing that this whole magic trick relies on changing magnetic flux, here is a classic curveball an interviewer will almost certainly throw at you. Why can't you just hook a transformer up to a direct current source? Well, the result would be pretty disastrous. DC provides a steady, constant current. That means after the initial switch on, the magnetic flux wouldn't change. And with no continuously changing flux, you get absolutely zero EMF induced in the secondary winding. But it gets much worse. Because a DC primary winding has very low reactance, it would draw a massive, dangerous amount of current straight from the source. You'd literally overheat and burn out the transformer in no time. All right, section 3, electrical machines and motors. Now, physically, motors and generators look incredibly similar, but you have to get this core directional distinction locked in your head. Motors consume electricity to create mechanical force. Think of the fan spinning on your desk. Generators do the exact opposite. They take mechanical force, like water spinning a massive turbine in a dam, and use that to induce and generate electricity. If someone asks you how a three-phase induction motor works, which is literally the workhorse of modern industry, don't panic. Just break it down into 5 logical steps. First, the three-phase supply creates a rotating magnetic field, or RMF, in the stator. Second, this RMF sweeps across the rotor conductors. Third, thanks to electromagnetic induction, EMF and current are induced in that rotor. Fourth, that new rotor current interacts with the original magnetic field to produce mechanical torque. And finally, step 5, the rotor starts spinning. It's a beautifully logical sequence of physics. Okay, let's shift gears to section 4, power systems and protection.
It's fascinating to see how elegantly a circuit breaker system actually operates. Most of the time, it just sits there quietly carrying the normal current. But the second something abnormal happens, a relay system acts kind of like the brain of the operation. It detects the fault and instantly sends a trip command. The circuit breaker then automatically isolates the bad section, saving the cables, transformers, and potentially human lives.
Of course, to protect the system, we need to know what those abnormal conditions actually are. Let's compare two major ones. An overload is exactly what it sounds like, just too much demand. Imagine plugging way too many space heaters into one outlet. The current gets too high, but it's still flowing along its intended path. A short circuit, on the other hand, is violent. This happens when 2 points of different voltages suddenly make contact, like if insulation fails completely. This causes a massive, extremely high fault current that has to be shut down instantly before it causes explosive damage. So how do we clear those faults? Usually with a fuse or a circuit breaker. A fuse is super reliable and cheap, but it literally sacrifices itself to save the circuit by melting its internal wire. It's a one-and-done deal. A circuit breaker, though, works as an automatic switch. It pops open during a fault, but the best part is you can just easily reset it once the danger is cleared, which makes it perfect for higher ratings and better control. Now, when we're dealing with extremely high-voltage transmission lines out in the real world, the air itself actually becomes an issue. If you're ever asked about the corona effect, here is exactly what you need to list off. Corona happens when the electric field is so intense it actually ionizes the air around the power line. This causes a bunch of specific problems: significant power loss, a really loud hissing noise, radio interference, ozone gas formation, and over time it seriously degrades the insulation. And that brings us to our final stretch. Section 5, Practical Engineering Scenarios. Let's talk about poor power factor. This isn't just some boring math problem on a whiteboard. It is a massive, practical headache for real-world engineers. A poor power factor forces the whole system to draw extra line current. What does that mean? Higher heat losses, annoying voltage drops, totally wasted system capacity, and, worst of all for a business, massive financial penalties imposed directly by the utility company. All right. Let's put you in the hot seat for some on-the-fly math. An interviewer might easily throw a scenario exactly like this at you to test your fundamentals. Say you have a transformer with 500 turns on the primary side and 100 turns on the secondary side. If the primary voltage is 200 volts, what is the secondary voltage? Did you get it? It's 40 volts. By just applying the basic turns ratio formula, you can quickly see the ratio is 5:1. So that 200 volts scales down perfectly to 40 volts. Being able to just snap off this kind of proportional math in your head is a huge advantage in any interview. Finally, I want to leave you with this really fascinating quirk of electrical physics. We know the motor's stator creates a magnetic field spinning at a specific synchronous speed. But why is it physically impossible for the induction motor's rotor to ever fully catch up to that magnetic field? Well, think about it. If the rotor magically caught up and matched that speed, there would be zero relative motion between the spinning magnetic field and the rotor conductors. And without that speed difference, which engineers call slip, there's absolutely no electromagnetic induction. No induction means no current, and no current means exactly zero torque. The motor would literally just stop driving itself. It's kind of a beautiful paradox, right? Perfect synchronization is actually the enemy of progress here. The motor literally needs a little bit of slip, a little imperfection to keep moving forward. It really makes you wonder, what other systems in life only function when there's a little bit of friction to drive them? Thanks for joining this explainer, and keep learning.